Hello, everyone. Welcome to another Kent Seminar Series. Today, we're all on Zoom because there's a complex weather situation here in Illinois, but I hope we're all safe and warm. Today, I have the honor to introduce Dr. Michael Elwardany. Dr. Elwardany holds a master's degree from the University of New Hampshire and a doctorate degree from NCSU, North Carolina State University. Personally, and everybody that works on asphalt binder knows Dr. Elwardany's work on asphalt binder aging during his PhD, and later on some other work he has been developing at FHWA. Now he's the contractor manager of the Asphalt Binder and Mixture Laboratory at the Turner-Fairbank Highway Research Center. And he's interested in pavement sustainability and resiliency through multi-scale and interdisciplinary research. So without further ado, let's welcome Dr. Elwardany. Michael, the screen is yours.
Sure, thank you. You can hear me and you can see the screen, correct? That's right?
Yes, that is correct.
Okay, perfect. Thank you so much. I really appreciate the opportunity. Thanks to Dr. Ahmed Al-Qadi and to Javier for inviting me to give this presentation. And thanks for your time and for coming to this presentation. I'm going to talk about a tale of two deltas. So I mean by two deltas, delta TC and delta TF. I'm going to talk about them. So those are two binder parameters. And the presentation is talking about proposed changes to asphalt binder specifications in order to address binder quality related thermally induced surface damage. So what we call it non-load related damage, damage coming from thermal fatigue, thermal loading, block cracking, in the form of block cracking, transverse cracking, graveling, all these issues. I want to start with acknowledgement to the various groups that contributed significantly to this work. This work started at Western Research Institute, where I used to work. It was initiated under the NCHRP 9-60 project. I'd like to acknowledge Jean-Pascal Planche. He's the CEO of WRI. Gail King is a consultant. And the rest of the NCHRP 960 team, WRI team, and the panel, they contributed significantly to these findings. Later, I moved to FHWA Turner-Fairbank Highway Research Center, where I worked with Dave Menching, he's the program manager. Also, Jack Huchef, he's the team leader, and Adrian Andresk, he's the binder lab manager. We have done extensive work over there as well on the same topic. And then also, I'm going to present today some of the work that we did with some of our collaborators, including Tom Bennett from Rutgers University. So the problem statement. There are significant changes that took place in the asphalt binder market after the development of the sharp super pave specifications in the 90s. As you can see that there are changes in crude oils in the process of processing of these crude oils and refining methods. Waxes in binders, air blown, oxidized blends, solvent deasphalted residues that go back to that are blended back with oils to form possible binders or binder additives. Various polymers have been developed, including reactive polymers like isocyanate based or epoxy modified asphalt or terpolymers, SBS, and various elastomeric polymers, and other modifiers and softeners. We have been doing recycling of asphalt materials, either RAP or RAS, or from pavement or shingles. And these recycled materials, sometimes with high concentrations, we add recycling agents and WMA technology. And we are proud that asphalt is the most recyclable material in the US and in the world. compared to glass. It's more recycled than glass or plastic or paper. So this is very good achievement from the industry. Also, we have industrial wastes like re-refined engine oil bottoms. So even the oil engine oils are residues from these refining or recycling go back to the asphalt market. Ground tire rubber, recycled plastics. We have biobinders, bioadditives. We have this broken residues. Those are produced by partial upgrading or pyrolysis process, where those were used to go to the bunker fuel, like used as bunker fuel, but because of new specifications on sulfur content in bunker fuel, some of this broken residues may go back to the asphalt market, among others. So as you can see, there are many different developments and opportunities and challenges that are taking place in the asphalt market. And this caused binder variability, which also led to inconsistency in the quality, and it doesn't necessarily captured by the current specification framework. So there is a need to try to find or propose some changes to the current specifications in order to address these factors. And of course, this binder quality affected the pavement performance. So as you can see, this is a survey. So the way we started our research is that we conducted survey with the help of NCAT. We contacted various agencies, as you can see, and we tried to map out the various factors or challenges that each state are facing in terms of non-load related cracks or thermal cracks. So transverse cracking, between 3 to 5 years from construction. That's a significant challenge, and we are trying to address this problem. So in the past 10 years, various researchers and the industry came up with different solutions to this. And they are basically, most of them are focused on rheological cracking surrogates. What I mean by rheological surrogates here is that they don't necessarily test the binder or the material until failure, but they do, in rheology, we do some sort of creep and recovery test or relaxation test or dynamic modulus, dynamic shear testing in order to come up with relaxation properties, which would contribute to cracking resistance, of course, in the field. And that's what are measured by the rheological surrogates. So some of the rheological surrogates that have been proposed in the past 10 years are the delta TC, which correlates to ductility and to field performance to some extent. And this has been introduced by Mike Anderson at AAPT meeting in 2011. And then you can see here ductility measured versus delta TC parameter. And you can see there is somewhat relationship between them, but this study was based on 3 unmodified binders. And then you can see that later, Glover also has a function here. So G prime divided by eta prime divided by G prime. And this rheological parameter that Glover came up with correlates also with delta TC and correlates with ductility. Later, Jeff Rowe came up with the Glover Rowe parameter, and basically he was able to turn this function, Glover function, into a function of G star and phase angle, so it's easily calculated by our testing methods. So this is the Glover Rowe parameter and the delta TC parameters, and both of them are doing a great job in order to capture relaxation properties and inconsistencies in binders or binders that are different from the norm. But most of these studies, as you can see, are proposed like 10 years ago, and they are mainly, at least when they started with unmodified binders, but later they started to include polymer binders. Now, the situation now is that in 2019, there was a survey done by Asphalt Institute, and it shows that at least 10 highway agencies, including Florida, Utah, Vermont, Maryland, Kansas, Ontario in Canada, Texas, Oklahoma, Delaware, and including also the Port Authority in New York and New Jersey. They all have included delta TC in their specifications, in their binder specifications. And you can see different aging requirements, different threshold, and the minimum delta TC requirement or the minimum delta TC varies between -2 and -6 degrees C at PEV 20. So Utah proposed -2 and Texas and Oklahoma proposed -6. So that's the range from the various states. And the current situation is that these states are, they use delta TC as part of their specification framework. So delta TC is good in for various reasons. First of all, it can capture some properties in the binder, including waxes. So this was actually 20 years ago. So 10 years before the proposal of delta TC, Robertson from WRI, right after sharp time, he proposed a relationship between delta TC. The term was not there at that time, it's just TC minus TM, which is delta TC at the end. So this is what we call delta TC now. And he showed in his report delta TC versus wax content. And you can see he divided binders to S-controlled and M-controlled binders, and showed that M-controlled binder or relaxation-controlled binders are the binders that have negative delta TC, and those are mostly high in waxes, or they are air-blown binders. So that's pretty good observation back during the sharp time. And then recently, Didier Leceur worked with us, with our group at WRI, and he showed that delta TC also correlates with R value from the master curve, from Christensen-Anderson model. And the conclusion here, so he came up with this equation, and the paper has actually exact derivation of this equation. And you can see this is a mathematical and fundamental relationship between R value and delta TC. And that delta TC equals 0 is equivalent to R value of 1.94. That's the rheological parameter from Christensen-Anderson model. The point here I'm trying to make is that first of all, it can capture some properties in the binder. And moreover, it can also, it could be considered as a shape parameter for the master curve. But of course, if I have to compare between R versus delta TC, I need to run full master curve to obtain R value. But delta TC is already, could be obtained from the BBR, which is already implemented in the current SuperPave specification. So that's why delta TC could be more convenient to some people. Next, so what we did in 960, we got a lot of binders with different properties. We tried to address the current market. So we collected unmodified binders, polymer modified binders here in red. Re-refined engine oil bottom modified binders. So those have re-refined engine oil recycled material. SDA, which is the solvent deasphalted blend. PPA modified, polyphosphoric acid modified. Biofalt, so that's from biomaterial, oxidized blend, and air-blown binders here, and visbroken binders. And you can see we looked at low PG grade, and you can see that most of the polymer modified binders have lower low PG. That could be because of the polymer, but more importantly is that we typically use softer base binders with polymer modification. So that typically lead to the lower PG for most of the polymer modified binders. So you can see in this map that most of the red binders are on the right-hand side where they have lower low PG. Next, we started to map those binders looking at delta TC after PAV 20 aging, so aging for long-term aging, 20 hours in the PAV. And what you can see, if minus 2.5 is the typical value or threshold for delta TC, you can see delta TC can capture some of the RUB modified binders, air-blown binders, vis-broken binder, AAM, which has high waxes, so it's a high waxy binder. So you can see it can capture some of these problematic binders. So basically anything below the line would be rejected and all the binders above the line would be accepted if we use minus 2.5 as our threshold for delta TC after 20 hours of aging. Now we did the same study after 40 hours of aging, and again we can identify vis-broken, oxidized, and air-blown binders easily. And then we did also a study on oxidative aging and physical hardening. So here we stored the material at low temperature for 3 days and measured the BBR data to come up with delta TC. And you can see now we reach to values that maybe you haven't seen before, around minus 30 delta TC for some binders. But that's after extensive aging and extensive physical hardening conditioning. So that's really like the worst case scenario, trying to see whether we can identify same problematic binders like vis-broken, air-blown, or oxidized asphalt or waxy binders. Next, the other thing we did is that we looked in the literature and we found a very nice study that was actually done at Total in France. And this study looked at 2 base binders. So this is a classical or commercially available binder, that's the blue one. And then the red one is actually red or oxidizable. So it's just a lab blend for the sake of this study. It's not commercially available. And you can see that the blue binder, base binder, is here in blue, and then the red base binder is here in red. The point here is that this is the base binder for the blue. It started with good delta TC, minus 0.4, so that's good. It's above minus 2.5 threshold. And then when we started to add 3% SBS or 6% SBS, so that's the polymer, the styrene butadiene styrene polymer, you can see that delta TC started to drop down. More importantly than that, when we started to add 3% linear or radial SBS, we have some drop in delta TC. But then if we do cross-linking, that delta TC would improve again. And so on with 6%, very low delta TC, as you can see here. If it's cross-linked, that would improve. So basically here, cross-linking could improve delta TC value and relaxation properties and the homogeneity of the blend. And the other thing is that, or the dispersity of the polymer. And the other thing is that regular SBS modified binder may have lower delta TC compared to the base binder. Also, if you start with bad base binder or base binder with low delta TC, then the polymer blending would actually exaggerate the problem, or like, it's gonna go even lower than the good base binder. So that is telling us that if we start with a bad base binder, polymer modifying it is not gonna help too much with relaxation properties, for example. And then we looked at the relationship of these binders. They ran actually FTIR microscopy techniques, and they found when we took this data and start to analyze them, we were able to find some relationship between the drop in delta TC for these polymer blends and the microstructure, whether those are homogeneous blends and those are physical blends, or they are not cross-linked, and you can see different phases, and therefore they have lower delta TC. So far, I showed that delta TC is a good rheological parameter. It's a good solution to identify some of the problematic binders with high waxes or vis-broken or binders that are prone to aging or physical hardening. However, they have their own limitations as well. So for the limitations, you can see here the Glover rho parameter here correlates well, or the Glover function correlates well with ductility. And this was shown in Glover report in 2005. But in the same report, if you flip a couple more pages, you will see this plot. This plot in the next chapter or so in the same report is telling us that ductility and Glover rho parameter, they don't correlate. This relationship is not universal. Those different binders with different trend lines, they are polymer modified binders. So for polymer modified binders, there is no universal relationship that would connect ductility with Glover rho or Glover function. And you can see here at the same value, you could get different ductilities depending on the type of polymer used. And the line here that falls below all the other lines, this one is exactly the fitting of the unmodified binders. So that tells us that rheological parameters have their own limitations when we start to study polymer modified binders. And you can see here, this is the delta TC parameter. You can see that we started, this is data that we collected from Sang-Soo Kim in 2007. We have 0% SBS binder, so that's the base binder, 2%, 3%, 4%, and 5% SBS. And you can see here that this red line is delta TC. Delta TC started with good delta TC from the base binder. Then as we started to add polymer, delta TC started to drop down, and that is a significant drop. That's going to -4 while it started from 1.5. So that's 5 degrees or 5.5 degrees drop in delta TC by adding 5%. That's pretty significant. And you can see that TCS didn't change much, but mainly TCM is increasing. So that's basically telling us that stiffness didn't change much, but M, which is relaxation, changed dramatically and dropped down dramatically due to the polymer or the elastic response that is added by the polymer modification. You can see here, this is the Glover rho parameter, and same story. We had 5 different base binders with different contents of SBS 2 and 4, and then different types of SBS, SBS-A and SBS-B. And you can see with this experimental matrix is that those are the base binders. This is the yellow line is the cracking, is the warning limit. The red line is the cracking limit based on the Glover rho parameter in the black space. As we get closer to the warning limit, so those binders are problematic. And if any binder passed the red line, that's basically failure. Or we expect that this binder is going to fail in the field. You can see this is the 0%. As we go to 2 and 4, more and more binders started to fall in this warning zone between the warning and the cracking limits. Previously with 0%, only one base binder was problematic. All the other base binders were good. But as we started to modify them, you can see that the X binder here started to get into the warning and cracking, closer to the cracking. So we have done different studies, and we collaborated with various groups to show again and again how rheological parameters are not suitable to be used only for, or to be only used as the single parameter to identify polymer performance. So how about the field? In the field, transverse cracking and fatigue cracking. If you look at what happened here is that we looked at different sections. Those are transverse cracking sections with polymer modified binder versus the equivalent section, so an adjacent section with control binder that is not polymer modified. So each data point here, this point means that the polymer modified had only 100 feet of cracks, the polymer modified one, but then the unmodified one had 250 feet of crack. So 100 versus 200. So all these binders or all these dots on above the line of equality are telling us those are the points that show that polymer modification help with transverse cracking resistance and help also with fatigue cracking resistance. So the field data is telling us that polymer modified binder is supposed to perform better. So here's the solution. The solution is to test the material all the way until failure. Binder could be the only civil engineering material that we use and use it and design for it without studying its failure properties. That's a big limitation in our current practice. So one of these solutions, and we're not proposing this as the only solution or the single solution, this is one of the solutions, is to test using the asphalt binder cracking test for the device. So basically, any kind of test that can test the binder all the way until failure. That's the point. You can see ABCD correlates well with TSRST, with the thermal cracking on the mixture side, with different polymers here. And this was developed by Sang-Soo Kim. The difference here is that when it was developed to replace BBR and to come up with the PG grading from this test. However, we think that this test is a failure test. It should be treated to actually, or used to replace the direct tension test that was originally proposed in Sharp time. That's the whole idea or the approach that we decided to take in 960 project. So the factors that are affecting ABCD cracking temperature are, this test is thermally loaded. The binder here is thermally loaded during the test. So there is no mechanical loading. We put the binder in a ring. There is a hole here in the sample. And then that initiates some stress concentration. And then, so we know that the crack will initiate in this area. And then we drop down the temperature until failure takes place. So the rate of, the strain rate or the displacement rate is actually a function of the coefficient of thermal contraction of the binder. That's very important to capture in the specification. So how much the binder is going to contract at low temperature or under a given thermal history. And then linear viscoelastic properties are important. We're not saying those are not important. Those are very important, G star and phase angle, because they define relaxation, the relaxation ability, and also the thermal stresses developed under a given thermal history. And then the binder strength, because that's when the binder is going to break. So that's the binder strength, which is another viscoelastic property. And here what we mean by viscoelastic property is that binder strength is a function of loading rate and temperature. So there is a viscoelastic component there. And also all these parameters are also affected by the glass transition of the binder. So as we go through the glass transition temperature for a given binder, all these parameters are going to be affected. So we came up with the delta TF parameter. So that's the second delta in the tale of two deltas. So delta TC is useful. It's a rheological parameter, but we came up with a failure parameter called delta TF. So F here stands for failure. And delta TF is the difference between TCS at 300 megapascal. So that's the BBR critical temperature based on stiffness, and the actual cracking temperature from ABCD. And in this situation, we had to normalize the cracking temperature because it's a strain control test. We had to normalize it to the glass transition temperature, which is in another form, glass transition temperature and temperature at S equals 300 megapascal strongly correlate with each other. But we have shown significant data, like a large database to prove this point. Both glass transition and TCS are temperatures at equistiffness temperatures. So they correlate to each other to a decent extent. And therefore we use TCS because it's already part of the specification parameters. So it's easily, it's readily available in the current system. So we just used it and we calculate the difference between those two, and that's the delta TF. So the physical meaning of delta TF, what does delta TF means? Delta TF basically is an indication of the strength of the binder. And what we mean here is that during Sharp time, because they were focused on unmodified binders, when they reach to 300 megapascal, that's the limit, that's the strength of the binder, that's the assumption. And therefore the temperature at which the stiffness reaches to 300 megapascal is a critical temperature based on the stiffness. because here we assume that most of unmodified binders actually fail at 300 megapascal. That's true. But now we have polymer modified and all various kinds of binders. So we actually capture the real or the actual cracking temperature by this test. And the difference between them, so if we have positive delta TF, that means that the binder reached to positive delta TF means that the cracking temperature was actually lower than the temperature at stiffness equals 300 megapascal, which means that the binder reached to this temperature and reached to 300 megapascal, but still didn't fail. It actually fails at lower temperatures, and therefore it actually failed at higher stress values, or it has higher strength, basically. So positive delta TF means higher strength, and it means it is also a function of CTC and TG of the. So that is important because part of our development that we came up with two thermally induced damage mechanisms. One of them is the classical one that we all have in our textbooks. It's the mix restrained, or what we call it external. Basically, the pavement is trying to contract at low temperature, and because it's restrained in the longitudinal dimension here, you can see that stresses will start up and then start to tensile stress is highest at the surface and then goes down. And you can see due to the tensile stresses here, the transverse cracking in the pavement will start to form like this. However, we also looked at the actual material at the mixture level. We found that the mixture level, even if we don't restrain the specimen from inside the specimen, if we quench cool it or do a very high cooling rate to the mix, the differential contraction between the mastic phase and the larger aggregate size particles could form some stresses that are high enough to cause damage internally in the specimen. So this was published, and we have discussed this using finite element analysis and actually mixed BBR specimens. And it was also presented by Sang-Soo Kim and Behnia using acoustic emissions and other test methods. We have done finite element analysis. You can see all the red parts here are the mastic phase here that reach to their strength. So those are failed. Those are the areas where stresses exceed the strength of the material. And that's why we think that the ABCD actually is doing a great job to simulate what happens to the binder under this mechanism of failure. Of course, it would be ideal if we use mastics, but at least the binder could capture part of that. So you can see we measured delta TF here. And you can see now we can differentiate between polymer modified binders, all the red ones here. And then we can differentiate between high quality unmodified and then lower quality unmodified binders. So we can capture basically the difference between polymer and non-polymer modified binders, or binders with high strength versus lower strength. And then we proposed a framework to analyze any binder using delta TC and delta TF. So both deltas are useful. Basically, delta TC can detect RUB, air-blown, visbroken, oxidized binder, but delta TF can tell us whether this is a modified binder with higher strength or not. So you can see that in this area, upper right-hand side of the curve or of this plot are the binders that have good delta TC and good delta TF values. And those are mainly 7% SBS. Those are the highest two binders here. And then as we go down, those are SBS modified binders and other elastomeric kind of polymers. And then you can see the unmodified binders and then the other binders that have either air-blown, visbroken, or oxidized binders, or RUB or SDE. Now, the point here is that if you only use delta TC parameter, all these binders in this narrow window have the same delta TC, minus 2.5 here on this line. But using delta TF, you can differentiate between kind of borderline delta TC values because they have polymer modification in them, or because they are lower quality binders and they are unmodified, but they have critical delta TC values. So you can differentiate between binders with the same delta TC value if you use delta TF. That's the idea. And here, back to the example of the delta TC with the different concentrations of SBS. If we use our analysis, you can see 0, 2, 3, 4, 5%. This is the cracking limit, or this is the limit, the specification limit that we propose for PEV 20 hours. Anything on the right-hand side would be accepted, and anything on the left-hand side would be rejected. And you can see that now, if you use 2.5 as the threshold for delta TC only, then 4 and 5% SBS, those 2 points would be rejected. But if you use delta TC and delta TF parameter, now you can see delta TC is decreasing with higher polymer modification, but delta TF can capture the additional strength added to those binders from the polymer matrix. So this is the proposed specification framework that we came up with. Basically, to simplify it further, we thought that if you have very high or very good delta TC, then you don't need to worry about ABCD tests. So you can just look at delta TC value. We run BBR already as part of the current specification. So you don't need to do anything extra. If delta TC is above -2, you can directly accept the binder. If delta TC came up lower than -6 degrees C, then you can directly reject the binder and you don't have to run ABCD for them. So that's a further simplification we came up with, that only for critical binders between -2 and -6 delta TC, those are the ones that we need to run ABCD for them to determine delta TF. And based on delta TF value, whether it's above the line or below the line, we can decide whether it's accepted or rejected. That's a further simplification because we don't need to run ABCD for all the binders in the market. Just very briefly, other failure parameters. We're not saying ABCD is the only feasible test to be used to study failure parameters, okay? So for example, this is part of the work that was done at Turner-Fairbank, FHWA Turner-Fairbank Highway Research Center. We compared between ABCD and DENT results. So DENT is a double-edged notch beam test. It's conducted at intermediate temperature versus ABCD at very low temperature. And you can see the difference is that DENT is mechanically loaded, but ABCD is thermally loaded. So there is a big difference in the mechanism of failure between the two tests. ABCD is affected by glass transition, thermal contraction, by physical hardening factors, phase-changing materials, waxes, all these things could affect, and some polymers actually affect the ABCD results. But also that ABCD measures low temperature strength, while DENT test measures the intermediate temperature strain tolerance. With all these disclaimers I put up front here, so I understand that there is a different mechanism in those two test methods. However, you can see that there is a correlation between ABCD and DENT test using various binders with high RAP and RES in them, so recycled asphalt pavement and shingles. And here you can see there is a correlation between, those are binders with different recycled plastics, for example. And you can see there is a relationship between ABCD data and CTOD from DENT. We have done the same study using HYMA, highly polymer modified binders with 7.5% SBS. And we have seen again the correlation. We have also done some validation, field validation for these test methods, but the idea is that you can use various test methods because if the binder is polymer modified, it will generally have higher strength values and higher strain tolerance. Of course, this relationship is not universal. So you will find some polymer modification or modifiers that may affect the strength at low temperature, but not so much on the strain tolerance. But the idea is that we need to go beyond the linear viscoelastic limits. We need to go beyond the rheological surrogates to actually measure the performance of the material. For forensic studies, at FHWA, we have various sections with different recycled asphalt pavement and shingles, high concentrations of them. And we load them with accelerated load facility here. It's a full-scale experiment. We collected field cores and we extract the binder and do some testing. And we tried to implement the same framework, delta TC, delta TF, on materials that have high RAP and RAS from the field, an extracted binder. The message here I'm trying to say is that you can see this is the version binder. This is it falls with good delta TC. And then all of these binders have bad delta TC because they have high RAP and RAS. We're talking about 40% RAP and 20% RAS, RBR. So this is very high concentration of RAP and RAS. But what you can see that this is the version binder. This is the control with 20% RAP. And then once we go to 40% RAP or 20% RAS, so high recycled material, they have lower delta TC and they have lower delta TF values. So you can see the trend. What we propose here is that maybe this same framework, of course, we will have to come up with new thresholds, but the same framework could be applied on forensic studies with high RAP and RAS, or it could be used actually in designing high RAP and RAS mixtures, or even 100% recycled material could be designed by looking into the failure parameters of the binder and the rheological parameters altogether. Finally, I just want to share an idea that we came up with also with analyzing data at Turner-Fairbank in collaboration with Tom Bennett from Rutgers University. He actually collected most of the mixture data. Actually, all the mixture data was collected by Rutgers University. So this is the SCB cracking test on the mixture side. This is developed by Dr. Ahmed Al-Qadi at Illinois, University of Illinois at Urbana-Champaign. So I guess most of the attendees here are familiar with this. And we were trying to see how the binder quality affects this test data and the mix design process itself. We found in the database like very nice experimental design here that gave us a lot of good insights. The difference, if you look at these binders, these dots, they are the same here on the right-hand side and left-hand side plots. Those are the same binders. So it's actually the location is the same. And here I'm looking at delta TC and dent. So the double-edged notch test, CTOD. Okay, so that's the strain tolerance at 25C and delta TC. Those are the exact same binders. The difference between left-hand side and right-hand side plots are that those two mixtures have different effective binder content. So the left-hand side has 12.2% effective binder content, the VPE, and then the VPE for the right-hand side is 14.5. What you can see here is that we decided to classify those binders with depending on the flexibility index value. So flexibility index 20 larger than 20, between 15 and 20, between 10 and 15. So every 5 degrees or 5 values, you can see that falls in a different classification. Now, we use the same color coding for left and right. The difference here is that if we have binders that have very low delta TC and very low strain tolerance, adding a little bit of more binder in the mix is not going to help much because those black are below flexibility index below 5 and they stay the same. However, if you look at those ones here, you can see we have orange ones between 15 and 20. We have the gray ones here between 10 and 15. When we change some parameters in the mix design, we can put them all in flexibility index above 20. So that is showing us that the same binder quality, we can look at the binder quality, how it affects the flexibility index, but at the same time, we can look at how much binder we can add, especially for the critical binders here that could improve their flexibility index and therefore the field performance as well. So that's kind of the framework that we tried to take. This is more data on delta TC and phase angle. Same story, just different ways of looking at the data, but you can see these ones have kind of average flexibility index. And once we change the mix design, we can actually achieve better flexibility index values. And same thing here with black space in and Glover row parameter in the black space. You can see that those black ones, dots here, those are bad binders, so the lower quality binders, and those have lower flexibility index values. But as you can see, those critical ones here, especially the gray ones here, once we look at, if we change the mix parameters, we can actually get them to be blue here. So they fall in the flexibility index above 20. So that's the whole framework that we started to look more into details of. We're not just talking about the binder quality, but how the binder quality could affect our mix design. We would like to look at balanced mix design more as a 3D thing, looking at not just binder content and trying to adjust binder content between fatigue, cracking, and rotting, but actually trying to capture also or put in this equation material selection and binder quality, because this could affect our design dramatically. So we need to think about the bigger picture as well. So by that, I would like to thank you all for attending this presentation. I'll be happy to take your questions and listen to your feedback. I'd like to also thank all the collaborators. We have done collaboration with Rutgers University, University of Waterloo, Nevada, Reno, VTRC in Virginia, and also various labs in Europe under RILAM. And we're open for more discussion and collaboration with various groups. So please let us know if you would like to collaborate with us in the future. Thank you.
Well, thank you, Michael. I think we have a couple of questions in line. I think we have time for a couple. So I have Professor Al-Qadi raising his hand. Professor, do you want to unmute yourself?
Yes. I guess you can hear me, right?
Yes.
Yeah. Okay. Thank you so much, Michael. That was an amazing lecture, and it gave truly good overview about where we are right now and what we have done. I have a quick questions. Now, when we are trying to combine the impact from the delta CF and the critical and so on together, don't you think that the geometry for the testing itself will play a role? Because when you look at the ABC test or ABCD test,
yeah.
Yes, you were maybe more thinking about like a shrinkage test in a way, which is following Komishenko's approach for calculating the stresses. And then when you mentioned about having the beam strain, I was more excited that you're going to be using this. And you said that the shrinkage test is more trying to consider the aggregate and the attachment to the aggregate. I mean, there is a way that we can separate this? Because I think it's going to be still geometric dependent what you are measuring, which, does that make sense where I'm going here?
Right. Yeah, definitely.
We have two geometries that we are trying to get something out of them, although I'm very excited about the idea, like if we're using just simply a beam for the shrinkage, and we are trying to see how this is attached to the material, maybe adding something regarding the surface energy, which will be adding to that. I don't know, I'm just suggesting here, but it's amazing lecture. Thank you again.
Thank you, Dr. Ahmed. I think, I totally agree with you. Those are very great points. I think in the DEN test, we don't have this effect that is coming from the geometry, because we run 3 ligament length and we apply full fracture mechanics approach to capture the CTOD, which is supposed to be a measure of that is not dependent on the specimen geometry. So dent test has this quality. ABCD is definitely going to be affected by the specimen geometry. And I agree, there are ways to overcome this. However, the problem, as in dent test, for example, is that people need to run 3 ligament length, and that would lead to, and need to run multiple replicates. So asking for 6 to 9 beams, including aging all this binder in the PAV could be not very practical and not very applicable to the industry. So that is something I think we need to balance between what we can capture, what we can improve on, but at the same time, what is kind of like between the fundamental approach and what could be applicable by the industry. So I think if we can come up with, that's kind of something I have in mind, is to come up with tests. And other people, I know Ramiz and others like Hamid Bazin and others have tried to come up with smaller scale tests that use smaller quantity of binder, apply fracture mechanics, and ideally we could run multiple dimensions or ligament length, and therefore apply full-blown fracture mechanics approach and come up with a parameter that is not sensitive to the specimen geometry. That would be ideal.
Absolutely. If I may, Javier, just one comment.
Yes, please.
Okay. Second, I think I'm very grateful that you did mention the disclosure about the difference when you were talking about including the dent test, because it's important for people to know that this is at the time that the material is completely viscoelastic, while the other could be at the elastic level. And the other comment I wanted to make when you mentioned about the iFit test, actually, what you mentioned today is really important, because we did have published that if you wanted to move your materials in the balance mix design to a better flexibility index, this is one of the methods that you do. So I'm glad to see that you did it in a different way to show that too. So thank you again for an excellent presentation.
Thank you so much.
I think we can take one more question. I think Professor Haj was the second one to raise his hand. Professor, can you go ahead?
Sure, I will go. Again, thank you, Michael, so much. This was really, really great presentation and really great for our students. I think this is, you fit a lot of information into a short time. So thank you. Really good work. And my question is about the strength, right? So you're getting a strength from ABCD that's purely based on the thermal stresses, right? With 0 mechanical stress. But in the field, there will always be a combination of mechanical stress and thermal stress, right? Accumulation in the binder. And this is based on the recovery period. Is this a difference? Do you feel that there's a difference due to that change, right? That difference in combined stress of mechanical and thermal in the field versus purely thermal stresses in the ABCD test?
Yeah, that's another very good point, Ramiz. I think that, the way how I could put it is that the material doesn't know where the stresses are coming from, whether the stress is coming from thermal loading or from traffic loading or combined between those two cases. The material is, it's going to be affected by the stresses, reach to the strength or the strain tolerance, and then start to break or to have failure at this point, regardless of the source of the stress, whether it's coming from one source or multiple sources. The focus of our study was more related to non-load related cracks, because we can see in some parking lots, like abandoned parking lots, that we can still see failure in the surface, although it's not been loaded that much. And that's why we were trying to look at block cracking, and even the field validation for this work was more focused on transverse and block cracking. However, I think in the reality, all this is taking place also under traffic. So yes, we need to capture all these things. The difference in ABCD test is that it captures what happens to the binder at low temperature, because we have physical hardening effects, we have crystallization, we have We have volume changes taking place in the binder. The wax component in the binder is changing its volume due to physical hardening. And some binders have lower TGE compared to others, and those would behave completely. Even the stress accumulation would change dramatically from one binder with TG around 0 degrees C versus another binder with minus 20 degrees C TG. You can see very different stress accumulation. So we were trying to focus on that a little bit. I think eventually, if we run a cracking test like ABCD, and we also use something like DEN test or LAS test or some other fracture mechanics test or continuum damage test at intermediate temperature, that would be ideal. Now you can capture mechanical loading and low temperature and everything, but then how much would the industry allow us to use? How many tests can we add to the PG specs? That's the only challenge, but I agree, of course. Thank you.
Well, thank you, Dr. Elwardany. Thanks everybody for joining today. We're gonna have to wrap it up here because we're a little bit over time. Dr. Elwardany's email is on the screen for the rest of the people that still have questions. And thank you, everybody, again. We'll see you next week with Professor Shane Underwood from NCSU. Thanks, Michael.
Thank you so much.